So let's take a look at exam 5, chapter 16, 17. These are probably in, I think they're most likely in order. Chapter 16 questions first, and then 17's. And some of this is going to be review from general chemistry. Let's see, I'm going to get that out of my way. That's still up there. Okay. Number one, which of the following corresponds to the greatest proportion of light absorbed by a sample? So greatest absorbed. The greatest amount of light absorbed would be the lowest transmittance, would right? The least amount. So if you got your sample and you got a certain amount of light here with intensity, what are they called? Initial? No. Well, for lack of a better term. And then out here you get intensity final afterwards. Okay, so if you ratio those two, the smaller and smaller and smaller value, that means this is getting smaller and smaller. So the greatest amount of light absorbed will be the smallest percent transmittance, which would be E, 15%. It worked better, but it'll help my feelings. I got a whole bunch of these. I bought them at Sam's Club.
Oh,
Got a big pack of them. Yeah,
they're nice.
it's cheaper than buying those little eraser things.
Yeah, they don't really work that well, anyways, because they get those little peelies.
Mm-hmm. And the only advantage to some of them is they're magnetized, so you can just stick them to the board. But
you could probably just glue or even sew a magnet in there.
Yeah, I guess. If I wanted to go to that much trouble.
Yeah.
Okay, number two. Which of the following stretching vibrations will appear at the lowest frequency? Okay, if we're talking about the lowest frequency, that would be the smallest energy, least energy. So the lowest frequency would also be the lowest energy. And the least amount of energy required to stretch a bond is the bond that's the weakest, right? And we generally describe weaker bonds as nonpolar bonds. So the nonpolar bond should be the weakest. The more polar the bond, the stronger it is. Okay. And we've got the difference between single, double, and triples. So we got to look at each one of these and say, all right. So actually, number two and three, right? 2 would be the lowest frequency. And let me do this. 2 would be the lowest frequency, and 3 would be the highest frequency. So I think we can do them both at the same time. So this would be the highest energy. Okay, so what do we have to choose from? We've got this bond. We've got NH and CH and CC and CO. Got carbonyl. Okay. So this is definitely polar, slightly polar, nonpolar. This one is the least polar of all the bonds. So it should be, these are in order. Roman numeral 4 would be that. So the strongest then would be as far as polarity goes, the difference in polarity here is this one. Right, this is the most polar bond. When we think of hydrogen bonding, that is the most polar bond to which hydrogen can attach to an electronegative atom. and it's either nitrogen, oxygen, or fluorine. So this is the most polar, and it's probably the highest energy, highest frequency. This one's slightly polar. And we might say, well, you know, that's a stronger bond. But in fact, this one gives us, I guess it's just, what does the data tell us? And the data tells that this one takes more energy than that. So that's Roman numeral 2. Yeah, well, it's like anything else. I mean, we can theorize all day long, but if the theory doesn't fit the data, then there's something wrong with your theory.
Yeah.
Okay, that was now we need number 4. Number 4. Okay, which of the following statements is true? Well, I got a typo there, don't I? Is true is not one word. Is it the same on yours?
What is it?
ISTRUE is one word. Number 4.
Oh, yeah.
Okay. The energy of a photon increases as its frequency decreases. No, it's the other way around, right? If we look at Planck's equation, they're directly proportional. As frequency goes up, energy goes up. So A is false. Okay, how about B? The wavelength of a photon increases as its frequency increases. Well, it's the other way around, right? Because the speed of light equals, well, let's see. Let's do it this way. The frequency equals lambda times speed of light, right? So then C equals frequency equal lambda. Does that make sense? Frequency is reciprocal. Reciprocal seconds. I think I got it backwards. And lambda is meters. Yeah, I got it upside down. So we put lambda on it. Let's do it this way. This is meters per second. So if we do frequency and lambda, this is meters, and this is per second. That's better. C equals frequency times lambda. Okay, so if we substitute for frequency here, then we got C over lambda. And if this is C over lambda, that means as the energy increases, the wavelength decreases. Is that confusing?
A little bit, but it's okay.
It's math.
Yeah.
Right. I'll look at it this way. If energy and frequency are proportional, directly proportional, then lambda's the other way. So as the energy goes up, the wavelength has to go down. That means that B is also false. The energy of a photon decreases as its wavelength decreases. Energy of a photon. No, it increases as the wavelength decreases. That's false also. Wavelength of a photon increases as its frequency decreases. Yeah, they're inversely proportional. Right, that's true. And the energy of a photon increases wavelength increases. Okay, so we found our answer there. All right, number 5. Which of the following would show carbon-carbon stretch at the lowest frequency in its IR spectrum? So the reason they're writing that carbon-carbon like that is so that we can include either sigma bonds or sigma pi's, double bonds. Lowest frequency would be also the lowest energy. Which one requires the least amount of energy to stretch? The one that is conjugated. Not just conjugated. If you've got some aromatics in there, that's definitely lower energy. So let's see. The only one that fits that bill is number 2, Roman numeral 2. Right? That should be the lowest frequency, lowest energy to stretch those bonds. Now, 1, 3, 4, and 5 are all bona fide double bonds, except for 5, and it's definitely a conjugated double. But still, actually, it would be, we'd eliminate everything but 2 and 5, and then which one is better? 2 is better than 5. Conjugated bond reduces the frequency some, and then aromatic reduces it even further. So B, Roman numeral 2.
What would be the highest?
The highest. Let's see. Number 3, actually number 3 has some conjugation in there. Yeah, number 3 has conjugation. It would be 1 or 4. 1, there's some conjugation there also. That cycloheptene. So I would say 4. Yeah, 4 would be the highest frequency. Those are independent double bonds. Yep. Yeah, that's right. 1, 3, and 5 are all conjugated. Actually, 3 would be even a lower. Actually, 3 would be better than 5. So if we put them in order, right, from low energy to high energy, right? So let's say energy is increasing that way and frequency is increasing that way. Then the lowest would be 2. Then the next one would be 3. Then the next one would be 5. And the next one would be, well, actually 5 and 1 would probably overlap. You might have difficulty telling them apart. And then the highest would be 4. Put them in order. That's a good test question. Okay. 6. Which of the following wavelengths corresponds to the photon with the highest energy? Highest energy, shortest wavelength. Shortest wavelength means highest frequency. So highest frequency would be the greatest energy. Shortest wavelength would be C, 318 nanometers. That's into the blue. We're pushing into the blue there. Let's see, 7 got split between pages.
Oh, it's really putting it down now.
This must be moving this way. When the concentration of an analyte increases by a factor of 3, what will happen to the UV-vis absorbance? When the concentration increases by a factor of 3. All right, remember the formula. Absorbance equals specific absorptivity, path length, concentration, those factors. So they're all directly proportional. This is increased, that increases, that increases, that increases, that increases. So if we take this one and increase it by a factor of 3, this is also going to be increased by a factor of 3. So C is the only possible answer out of that one. All right. Number 8. Which of the following would show the carbonyl stretch at the lowest frequency in its IR spectrum? Carbonyl stretch. And we want the lowest frequency. Lowest frequency. Lowest frequency. Least energy. Lowest energy. Okay. What would decrease the strength of that bond? Well, if we get some, and I always forget the term for this. I need to write it down on a card and just keep it with me. Can't remember the word. If we draw electron density away from that bond, it'll weaken it. Okay? So if we have another electronegative atom attached to this carbon, it will weaken that bond. And out of our choices, well, the lowest, a lower frequency, the highest frequency is going to be number one. That. Actually, no. Then this. Wrong direction. With a carbon, with a methyl group back. And then, let's see, we get some resonance. Yeah, we get some resonance would help us some. Here. And then lower the frequency even further should be lowest frequency. Oh, no, I'm sorry. Resonance gives us the lowest frequency. Yeah, that stabilizes the molecule even more. Frequency. Carboxylic acid and I'm having trouble today. Must be the rain.
Making everything foggy, huh?
Yeah. All right. Moving on. The lowest frequency is going to be number 3 because of resonance stabilization. Lowest frequency. Hold on a second. Lowest frequency. Okay, I'm thinking backwards. Lowest frequency is the least amount of energy. Smallest wave number would be the furthest to the right, correct? That's lowest energy, lowest frequency, smallest wave number. So the most stable bond is going to have the one to the right, least amount of energy. I'm thinking in reverse. The highest frequency or the largest wave number is going to be the one that I was talking about earlier, where we get, we're drawing electron density away from that. And takes more energy to stretch it. Which would be a carboxylic acid, number 4. And that occurs in the neighborhood of 3,300 wave number. With the alcohol, remember the alcohol stretch is going to be, it's going to look kind of like this, really smooth. And then when we do the OH stretch in the carboxylic acid, it's going to get kind of jagged with that. But that's talking about an OH stretch, not a carbonyl stretch. Carbonyl occurs farther to the right. All right. Induction. That's what I was trying to think of, the inductive effect.
Oh,
There was another one that I tried to think of and couldn't get it. And just when I think of it, I'm gonna write it on the board.
you need a badge of all the words you forget. That way you can just pull your little badge out, look, and
Yeah,
let it sling back.
right. Kind of like my dad used to wear one of those spring-loaded keychains
Yeah,
where you pull out like that. Nowadays, you almost don't need them because everything's wireless.
yeah.
Which of the following would you expect to have the longest lambda max? Which one would have the longest wavelength, be the lowest energy? And that one, we're comparing just doubles and single bonds, and this one is going to be the most conjugated. So the more conjugated bonds you have, the lower the frequency, and not longer the wavelength. So that's what moves molecules that have just a couple like that are going to be absorbing in the ultraviolet. But if we add, the more of these that we add, we're shifting into the visible to where you get things like beta carotene, which has 30 carbons, I think. No, 40 carbons, and half of them have double bonds. Then you're going to move into the orange. And for the carotenoid pigments out of lobsters and crawfish, you move into the reds because we get these things like that and this, and you get more conjugation there. It shifts the wavelength further into the red.
I read a thing the other day. It said that West Virginia has the most blue crawdads
Blue crawdads?
in the US,
Ah, yeah,
which I've seen a few blue
Yeah.
ones.
they'll be blue until you throw them in a pot of boiling water.
Yeah,
Then they turn red, don't they?
yeah.
I think what's happening is the carotenoids are bound to other molecules like proteins.
So is something like, why is West Virginia the most so? Is it just because something they eat? Is it their genetics? I mean, what caused them to be more blue here?
Well, I'm not sure if they're the same species as the ones we used to harvest in Louisiana. Forgot their scientific name now. Procambria clarkii, I think. They might be a different species.
Yeah.
10. Yeah, 10. Okay. Which of the following wavelengths corresponds to the photon with the lowest energy? Well, the longest wavelength is going to be the lowest energy because it's the longest wavelength is the highest. Let's see, longest wavelength, high wavelength, lowest energy. Lowest energy should be the smallest frequency. Right. So largest number for your wavelength, lowest number for your frequency gives you lowest energy. Yeah. So E would be the answer for that. Okay. What kind of vibrational mode is this one? Where you get the two hydrogens on that oxygen are shifting, they're stretching, but in opposite directions on a time scale. They're doing like that. That's an asymmetric stretch. Let's see what's happening with 12. Which of the following would not show any peaks at frequencies higher than 3,000? Higher than 3,000. Higher than 3,000 is an OH region, isn't it? Okay. Here we have you know, peaks at frequencies higher than 3,000. I thought that OH stretch would be higher than 3,000.
I'll look it up.
Not show any peaks higher than 3,000. Okay, okay. So we get OH, right? That's definitely higher than 3,000. We have NH, like that group, right? And a primary amine. Well, this is an amide. There you go, amide. And excuse me, that goes to carbon. Then, okay, so there's your amide, and you get stretches, the primary amines, right, where you have yeah, two hydrogens. OH on your carboxylic acids, and there's another primary amine, right, at the end of this chain. Right, they will be greater than 3,000. You know, and the that one greater than 3,000. Right. This is a secondary amine. You're still going to get them a little just above 3,000. But the tertiary amines, you know, this, I'm approaching this the wrong way. Well, okay. It won't show any peaks higher than 3,000. There are no hydrogens there. Right. This is carbon, right? So you're definitely not going to get any stretches there. Higher than 3,000, the bigger the atom attached to the molecule, the lower the frequency. Right? It stretches at a lower frequency, and you can see that with like a guitar string. Right? If you have two guitar strings, right? Well, I don't play guitar, but I think there are 5 of them, right?
Yeah.
Okay. And this one is the smallest, right? The highest note. Like this. This is the highest note. This is the lowest note. This one has the highest mass for its length. So the larger the mass, the lower the frequency of vibration. Same thing can be applied to molecules. So make this higher mass than a hydrogen, it's going to vibrate at a lower frequency. That's assuming that they're all at the same tension. Right? Tension has something to do with it too. That's why when you're tuning your guitar, you see it twisting that thing.
Yeah.
Twisting the keys.
Yeah. It's the keys.
Yeah, keys. Does your boyfriend play guitar?
I used to play violin.
Oh, okay, okay. Yeah, I was a wind instrument myself.
It didn't last long because I broke my arm like
Oh,
a few months into the practice. So.
yeah. That's unfortunate. Yeah, I had to put my saxophone up when we started keeping fostering infants. There was no practice time.
Yeah.
Once you get them to sleep, you don't want to wake them up.
Yeah.
So which of the electron transitions, and we'll have to look at the next stage, show in the figure below would correspond to UV-Vis absorption band of the shortest wavelength. Okay, we're looking for the shortest wavelength. Short wavelength is high energy. Short wavelength is the highest frequency. So when we're talking about UV vis, that's electron transitions, atomic electron transitions from different orbitals. So the absorption for the shortest wavelength, for the highest energy, would be the greatest gap between energy levels. So we look at our choices here, number 5, right? That's the biggest transition. Yeah, E would be the answer to that one. Right. 14. Which of the following should show carbonyl stretch at the lowest frequency in its IR spectrum? That is, lowest frequency would be the longest wavelength, shortest wave number. Carbonyl stretch. Okay. Lowest frequency, the least amount of energy required. Let's see. Well, we know that the carboxylic acids are way up into the 3000s. So 5, and I still can't remember. Carboxylic acid, ester. The esters are not too far behind. The aldehydes, number 2, and the ketones are a little bit less than. So I would think that the carbonyl stretch, if we attach, I don't have a good explanation for that because I'm not too proficient.
Yeah, this is similar to that other one too.
Yeah, sort of. Now we're looking at the carbonyl stretch rather than the hydrogen stretch. So I'll tell you what, let's look at the did I put that in here? No. Let's scroll down. Let's see, come back to 14. All right, let's go down and look at, I think I've attached. Yeah, I've attached here. Okay, so these are the regions. Single bond stretching with hydrogens. Q would be anything attached to a hydrogen. Triple bond stretch, double bond stretch. Okay, so the double bond stretches are right in here. And that could be anything. Carbon-carbon, carbonyls. Let's see. Actually, carbon-nitrogen. So if we look at it that way, then all we have to do is reference this higher energies required here for triple bonds. Double bonds are in this region. So if we go back to 14, come on. Oops, not going to do it. Back to 14. Here we go. Well, that didn't help me any. These are all going to be in the same region. So we need, what's the effect of NH2? What's the effect on attached groups? All right, so we need to, maybe there's another one down here. I think I did. Another, okay, we know we're in this region. We want the one that brings us the lowest wave number, right? Lowest frequency?
Yeah.
Okay. So let's see if we can find, nope. Okay, here. All right. So here we go. Lowest frequency is going to be amide.
That's what it's saying.
Okay.
Yeah, the amide is.
Amide, then carboxylic acid, then ester, then ketone. So that's what I would do. I would just look at the chart. And 14. Here we go. So the amide is going to be the shortest, the lowest frequency, smallest wave number. Okay, which of the electron transitions shown below correspond longest wavelength? The longest wavelength would be the shortest jump, right? So I'm not sure why we put these out here because they don't have a number. The ones that are numbered, the shortest jump is number 2, would be B. 16. Okay, what are we looking for here? Most consistent with the following IR spectrum. You know, the giveaway here is activities, the OH stretch in the 3000 region. That's not a smooth stretch that you would find from alcohol. Alcohol will give you a smooth at about 3000, 3300. Carboxylic acid gives you that appearance. So that's where I would go with it. Number 2. Now, there are probably other clues in here, right? Do we get a carbonyl stretch? Yeah, it's right in here. There's a carbonyl right there. So carbonyl combined with the OH appearance there would give you carboxylic acid. I think that's what the authors are getting at for this one. Let's see. 17. Which of the following would show carbonyl stretch at the highest frequency in its IR spectrum? Let's see, which was the highest was ketones. Yeah. No.
Carboxylic acid.
No. The
I can't
highest
remember.
frequency would be the highest wave number. It says ester. Hold on a second. 17. I'll come back to 17. Let's go down and look at our scale again.
I thought we said ester was the lowest.
I know. Carbonyl, ketones and aldehydes. Ester. Okay. Okay. Yeah, they're not really in order here. I thought they were in order. 1630, 1710. So the ester is between 1730 and 1750. Ketones have a wider stretch, wider range, 1680, 1750. Okay. So I guess with that in mind, we're looking at a narrow band between 1730 and 1750, and that guarantees that it's going to be the highest wave number, the largest wave number, or highest frequency. Okay, well, okay. How about 18? Huh? 18. Following molecule absorbs light at 455 nanometers in the blue region. 455. This is max absorbance. 455 nanometers. All right. What color does this compound appear? Okay, this is where you use the complementary colors. So what's complementary to blue? We have to go down to
Yellow.
well,
Orange.
where is it? I put it in first. Oh, it's not there. Okay. I need to be sure that one's included. Yeah, the complementary color for blue is orange. So this would show us orange as a complement to blue. I need that that pie chart.
Yeah. The color wheel.
Yeah, the color wheel. Yeah, that needs to be included on the exam. Here it is. Right here. I haven't printed out a copy of that yet. I'm not sure. Oh, maybe it did. Hold on a second. See if it's included. Uh-oh. Write myself a note. Okay. Of course, this one shouldn't be too hard because it's beta carotene, right? You know, beta carotene's orange.
Yeah.
Following vibrational mode. This is a symmetric stretch.
Those are
number-
fairly simple.
Yeah, that's an easy one. Which region in the IR spectrum could be easily used to determine whether the following reaction had taken place? If it's taken place, you're going to produce product, right? So you're going to get a triple bond stretch. That carbonyl, excuse me, that nitrile group, C triple bond N. That will be an indicator because you don't have that in the reactants. You know what? If you treat that bromide with sodium cyanide, couldn't you pick up the cyanide from the sodium cyanide? I would think you could pick up some of that. So maybe you would have to see an increase in the cyanides, the carbon nitrogen triple bond stretch to see that the reaction proceeding. You're going to get a signal anyway from the sodium cyanide, I would think, unless you get a shift from the cyanide ion versus the cyano attached to the molecule. I bet that has an effect also. So you'll be able to pick it up as a different peak rather than the free cyanide ion. We would have to ask somebody that actually does this for a living. But the answer to the question is triple bond region. Which region IR could easily use to determine whether the following reaction has taken place? Oh, okay. All right. This will be a double bond region. Definitely. That one's fairly straightforward. Which of the following corresponds to the least proportion of light absorbed by a sample? The most transmittant is the least absorbance, right? 90% transmittance. Draw the symmetric NH. Draw the symmetric NH stretch that would occur in the following molecule. I presented this as a double arrow on each of the bonds, but that's not really the best way to present it. If we're looking at this molecule, hydrogen there, then we should say that we get this and that one. This is a symmetric. Okay. So we increase the length of the bond, saying it goes this way, and then we get this one with a shorter bond. And we give it the arrow that way. That would be the proper interpretation.
Both of them.
Yeah. Because the way I put it in the in this slide with just a double barbed arrow, it could be going asymmetric also.
Yeah.
Which of the following two isomers would exhibit a strong carbon-carbon stretching absorbance band. A strong carbon-carbon stretching absorption band. The isomer with the terminal alkene would exhibit a stronger carbon-carbon stretch. This is using the symmetry rule. The more symmetry you have around a carbon-carbon double bond, the lower the energy. So if we have something like this, right, it's perfectly symmetrical. This side of the double bond is about the same as that side. This would be a lower energy situation. The higher frequency is the one where you have a lot of asymmetry. So if we do like this, that, then we have, now here we just have a sp2 hybridized carbon. And we have this 1, 2, 3, 4. We have this butyl side over here is asymmetric. So that gives us a requirement of more energy. So the higher frequency of that stretch would be B. All right. 25. Which of the following two isomers would exhibit a stronger carbon-carbon triple bond stretch absorption band? This same reasoning here, right? The symmetry, right? B is more symmetrical around that triple bond than A is. So A would require the highest energy. Stronger triple bond stretching absorption band. Hold on a second. Right, we're not talking about a frequency shift. We're talking about intensity, right?
Yeah.
Stronger stretching absorption band. Okay, we're talking about intensity here. That's my mistake. The intensity of the stretch. You would still get the carbon-carbon double bond position at approximately the same Wade number. But the strength of the stretch, the strength of the signal would be greater for the asymmetrical one. And same thing for 25. So you get the signal would be at a carbon-carbon triple bond region, but the peak would be much stronger. Okay, label this graph for a UV visible spectrum, right? The Y, let's see, we're at 26. The Y-axis would be absorbance, and the X-axis would be wavelength, usually in nanometers. Nanometers gives us whole numbers. If we use the international system, then we would use meters. Right? But then you'd have a fraction. You'd have to use a scientific notation. So we use nanometers. It uses with whole numbers. That's typical for UV vis. Let's see, 27. Describe how you could use IR spectroscopy to distinguish between the following two isomers. Well, let's see. They both have OH stretches. Yeah, they both have OH stretches. The carboxylic acid, and they both have carbonyl stretches. So let's see, compound A should exhibit a carboxylic acid stretch at around 3,000. Yep. and it would have an odd shape to it. It wouldn't be a uniform shape. This peak would be less clearly defined than an alcohol stretch, would likely overlap the carbon-hydrogen stretches in the same frequency range. Compound B contains an aldehyde and an alcohol. The OH stretch would be centered at around 3,300, so it's a higher frequency. Okay, would likely be well defined. Additionally, the aldehyde stretch in compound B would likely appear at a slightly higher frequency than the carboxylic acid stretch. Okay. That would be a lengthy answer. That looks like, if anything, an extra credit. Yeah.
Probably one that I won't do.
Okay. Yeah. That's a little more in depth than we were shooting for in this course. Okay. Calculate the concentration of a sample. If the sample absorbance is 0.68, the molar absorptivity is that value, and the length is 1 centimeter. Okay. So we go back to, let's see, number 28. We go back to this expression, length and concentration. So if we know the absorbance, right, absorbance units, and the path length is in centimeters, and the concentration is unknown, and the molar absorptivity, I didn't leave myself enough room here. Molar absorptivity is 8,400. And this is reciprocal centimeters. So this means they're in the denominator. Molarity in the denominator, centimeters in the denominator. Length of the cell is 1 centimeter, right? So this centimeter cancels that centimeter. This concentration, this absorbance, and if these are the correct units, if these are the units, molarity, inverse molarity, molarity, inverse centimeters, centimeters, then the result will be absorbance. And if the concentration is in molarity, that means that all these terms cancel out. And absorbance is a dimensionless number. We put absorbance on there because we can't just say 0.68, which is really what it is. We say absorbance because it's based upon this formula. Okay, so once we know that value, if this is in absorbance and these values are given, in fact, we could use anything in here as long as the concentration units are canceled out by this value and the path length is canceled by that value. So they have to match up. Right, now we can solve for C, would just be 0.68 absorbance divided by 8,400. Well, actually, we already canceled that before we brought it over.
Didn't we cancel out the molarity too?
No. No,
we didn't, because we're okay. Yeah,
that's the unknown.
Yeah,
right. This is in molarity. So we got to have molarity on both sides. Yeah. Since this is in the denominator, now the molarity is in the numerator.
Yeah. Okay.
So we just divide 0.68 by 8,400, and we should get 8.1. 8.1 times 10 to the minus 5 molar. Now, as a practical matter, we never do that. We set up a calibration curve. We have known values of concentration, right? Whatever they are. And then we have absorbance measurements, whatever it is. Then we plot that here. Right? There's our calibration curve. Then we go take our unknown and we find the absorbance of our unknown. As long as this doesn't change and that doesn't change, then these are linear response. And we say, okay, now we're going to read the absorbance of our unknown. Right, it's over here. That's our concentration. Now this is linear through a certain range. After you get really high concentration, it goes flattens out. And down here, it's a little difficult to, you have probabilities that are too wide. So you want to get in this range, mid-range. All right. 29. What are two basic types of vibrational motion in IR spectroscopy? Stretching and bending. Bending, that's the one I couldn't remember.
Oh, yeah. I remember.
Okay, 30. Nuclear magnetic resonance spectroscopy, NMR, is generated using which type of electromagnetic radiation? Radio waves. Nuclear magnetic resonance. Oh, that's a good key. Nuclear magnetic resonance radio. Now, the key to doing NMR is placing your sample in a strong magnetic field, right? Anywhere from 1.5 to 5 Tesla. Then and only then will the sample absorb in the radio range. Otherwise, the random orientation of the nuclei cancel each other out. And even then, the strong the magnetic field will have no measurable absorbance in the radio region unless you have an odd number of nucleons, odd number of protons or odd number of neutrons. So you have to have those two conditions, the odd numbers and the strong magnetic field. Then you can irradiate it and form a spectrum, an absorption spectrum. Okay. Now let's see, which compound would produce the following hydrogen NMR? All right. So let's look at our spectrum. We've got 1, 2, 3, 4. We have 4 chemically unique hydrogens, protons in that spectrum. So we've got to have 4 unique hydrogens in those molecules. All right. Let's take the time to actually draw them in here and look at it. That's a bromine. So we have 1, 2, 3, 4 carbons. That's Roman numeral 1. 2 is let's see. Yeah, up, down with carbonyl. Okay. 3 is up, down, up with some aldehyde. And 4, might put 5 off by itself, is a carboxylic acid. That's carbonyl, and this is a hydroxide. And then 5 is a ketone. Okay. Now, unique hydrogens. This is methyl hydrogens. So we have, that's a unique one. This one, we're going to have, let's see, carbon 1, 2, 3. We have 2 hydrogens here. Those are unique. Let's start from this side. The further they are away from the bromine, the more difference there are in the hydrogens. So these 2 are going to be unique. These 2 are going to be unique. These 3 are going to be unique. So we have 4 signals here, right? 3, 4. Based upon their distance away from the bromine. That gives them a unique character. Okay. Let's see, we're gonna have 3 here. We're gonna have 2 there, none there, and 3 here. But these 3 are close to that carbonyl. They're going to be unique. They're going to be different than these over here. These are going to be unique. These should be unique. So we got 4 there. The distance away from that carbonyl, we've got 1, 2, 3. We got a hydrogen here. We got 2 there. We got 2 there. And the distance away from that hydroxyl gives them a different shift, chemical shift. So you've got these are the same, but unique from the others. So there's 1, 2, okay. All right, we got 4 there. How about here? This one is unique. Let's see. Yeah. 1, 2, 3, 4. The none there. We have 2 here. And we have 3 here. 1, 2, 3. Count that one out. There are only 3 signals there. Okay. How about this one? We got 3 hydrogens here, here, and here. This is a symmetrical molecule. So these hydrogens are the same. And these are also the same. They're chemically identical. Right? So that one only has 2 signals. Right? So we can count 4 and 5 out. But now we've got to decide these guys. All right. So we've got a triplet, a quartet, and another triplet, and a singlet. Right? A singlet means that there's only 1 hydrogen in the neighborhood. Right? So do we have any of those where the signal from one of these has only 1 hydrogen in the neighborhood within 1, 2, 3, within 3 bonds? Right, so we have this hydrogen, there's bond 1, 2, 3, 4 bonds. No, that won't work. That would produce a doublet, and this would produce a triplet in this one, doublet in that one. So that's probably not our molecule.
We canceled that one out already though.
Oh, thank you. I could have had a V8. Okay, so let's look at this one. All right, this is 1, 2, 3. Okay, this is within reach. So this is going to produce a singlet. No, this is going to be split into a doublet. This is going to be split into a doublet. That one's a doublet. This is going to be a triplet. So we have a doublet. We have a triplet. Right, we only have 1 triplet. And this is going to produce, no. This is going to produce a quad with this one. This is going to produce a doublet with that. No, excuse me. N plus 1. All right, N plus 1. So 2 plus 1 is a triplet. This one will produce a triplet from that one, and that one will produce a triplet from that one. And they're different. So we're going to have 2 triplets. And this is going to produce a doublet. This is going to be complex. Right? We don't have any complexes in there, do we? No. Okay, so we're not. We won't have a combination from this one and this one that makes it complex. Right. So it's probably not that one. What if we start from this end? All right, we eliminated that one, and this one. Let's start over here. So this signal is going to be split into a triplet. And this signal is going to be split into a quad. But it also should give us, right? Is it 2? Yeah. right? Because this one is going to be complex also. If we look at this one, right, it's 1, 2, 3, right? So this one's going to be set off by itself. This is going to be a singlet, right? It's not close enough to be split by any of these. Okay. This one's going to be split by that one into n plus a triplet, right? N plus 2 plus 1. This one's going to be split. This would be complex, wouldn't it? Did I draw that one correctly? Yeah. Okay. So we got the singlet. Well, okay. We've only got one of these that's going to give us a singlet. No, but we eliminated that one already.
Yeah.
Right. So this is the only one left that gives us a singlet. Right. So there it is. Yeah. But I'm still concerned, why didn't this give us a complex signal? That one should be split into a triplet also, but it's got these 4, which should split it into a quintet. No, 3, 4, Q. So we get a triplet and a Q from that one. 1. This one's going to be split into a triplet. All right. All I can say is it's an art form. This is not, organic chemistry is not pure science. Actually, most chemistries are. But organic chemistry really sets itself apart as it's more a culinary art than it is a science. Okay, 32. That one, 31 was a process of elimination. Which of the following statements about nuclear spin and NMR signal is not true? Okay, so they're all true except for one because we don't have any oddballs in there. Nuclear spin generates a small magnetic field. Yes, it does. Just like electron spin creates a magnetic field, nuclear spin does also. So A is true. C, D, and E. How about B? A proton has 2 spin states. Yep, just like electrons up and down. C, NMR active nuclei must have an odd number of protons. Not necessarily, but they could have an odd number of protons, but they could have an even protons and odd numbers of neutrons, right? All we need is one example. Hydrogen, well, no. Helium. Okay. Helium, that would not be active, but that would. 3 neutrons, 2 protons. I don't even know if that's probably an isotope. More likely this one with 2 protons and 1 neutron. I'm not sure about the abundance. That's the question. So we found our false one. And D and E should also be true. Absorption of electromagnetic radiation causes a spin flip. Yes. Yeah. No NMR spectrum is generated in the absence of external magnetic field. That's also true. Without the magnetic field, you don't get a separation of alpha and beta energy states. And that's where they spin flip. They spin flip from one alpha to the beta and back and forth. Okay, 33. How many chemically distinct hydrogen atoms are in the following molecule? We looked at one like that before, right? Those on the end are identical. They're symmetrical to the bromine. And then the number 2 and number 1, 2, and number 4 carbons, 2 and 4 carbons have identical hydrogens. And then there's one in the middle, right? Because 4 bonds for each carbon, we've got a carbon, this is secondary, we've got a carbon on one side, a carbon on the other side, a bromine, and then there's room for 1 hydrogen. So we've got 1, 2, 3. We have 3 unique, chemically unique hydrogen atoms in this one. 34. That wasn't number 3, that was number 33. 34. HA. So we've got our hydrogens are labeled HA and HB. There are other hydrogens in there, but they're not labeled. So we're comparing the A and the B. HA splits the NMR signal of HB by 7.4 hertz. So the what's the terminology for that split? Signal split. No, there's another term for it. Okay, wait a minute, those are carbon signals. Okay, here's a splitting diagram. All right, what I'm looking for is
I need to take this phone call. I'm gonna step out just for a second.
okay, sure. Well, I'm trying to find the right terminology. Coupling constant. Coupling constant. That's what we're looking at. Coupling constant is the distance here between these split peaks. That's the coupling constant. Okay, so if HA splits HB with a coupling constant of 7.4, what should HB split HA? Same amount, exactly the same amount. So 7.4 hertz would be the answer, C. Coupling constant. I better write that over here. In case I need it again. All right. $35. Which hydrogen type has the greatest integration value? The greatest integration value. Okay. Are we talking about the greatest shift? The greatest integration value? No, I'm sorry. The greatest area under the curve. That's what we're talking about. When we integrate the area under a curve, which one of these should have the greatest integration value? Okay. Let's see. Now we're getting over into the field chemical shifts. Greatest integration values. Here it is. Um, the greatest integration value. Well, the greatest integration value is going to be the largest number of unique hydrogens, right? So which one has the most number of hydrogens that are unique, right? A and B, they're in different positions relative to the side group, right? So A, B, and C should be unique, right? They would be single signals. D, how many hydrogens are there on that carbon with hydrogen D? There's 2 of them, right? Okay, so they would be greater than C, B, or A. And then E is a methyl group. So there are 3 E's. So HE should be the greatest integration value because there are 3 hydrogens there that are unique. Okay, does that make sense?
Yeah.
Okay. All right, 36. 6. The lesson for me is don't wait 7 years to teach this again. Right? Teach it again next semester so it'll be fresh. Let's see, I need another marker. There. Here it is. Starting to fade. 36. What is the expected splitting pattern for the indicated hydrogen? Okay, that hydrogen, let's just draw this part of the molecule. Let's see, there's a carbon here, and there's a hydrogen there. Now, obviously, there are 2 others. But this hydrogen signal is split by only 1 hydrogen here, right? 1, 2, 3, 4. So it's going to split into an N+1 or doublet. 37. Estimate the value of the chemical shift for the indicated proton. Okay. This is a real test. What's the chemical shift for this indicated proton? I don't even know if I could do this. That proton is once removed from the phenyl group. All right, okay. So we've got this proton. How many of them are there? Actually, 2 of them. And we've got chlorine there, a chlorine there, and there should be another hydrogen right there. And then this is attached to phenyl group. Okay. So this is within, let's see, there's a hydrogen here, hydrogen there. So is this, that hydrogen is still influenced by that phenyl group. So what we're starting with,
It's because the 3.1 ppm falls within the typical range for proton adjacent to chlorine atom.
oh, all right. Yeah. Chemical shift. Okay, so they're just looking at the table. They're just looking at the shift from chlorine and they're not considering anything else. Oh, that doesn't make any sense. I mean, if they've got influence of that hydrogen once removed from a phenyl group, you should see a shift there also.
It says that chlorine is an electronegative atom, which will deshield the proton, causing the chemical shift to appear downfield in the NMR spectrum.
Okay,
Generally, protons are on carbon atoms adjacent to chlorine atoms have a chemical shift in range from 3.0 to 4.0 ppm.
all right. Well,
This is what my phone's saying.
I'm gonna leave that to the experts because we've got multiple influences there.
Yeah.
Right? We've got deshielding from the phenyl group also. I mean, it's not as big, but it's still there. So don't give this problem to me because I'll get it wrong. Right? I'm going off of the influence of both the phenyl and the chlorine. All right, so we throw 37 out.
Okay.
38. How many distinct signals are there in we've got ether. This is an ether. So I think this one's probably unique also. And then we've got this carbon. Well, that carbon is unique. This carbon is unique in its position. We've got these two should be influenced the same. Right? 5, 5. These two should be influenced the same, 6, 6. And then what we did that one. 39. Which of the indicated carbon atoms will be most deshielded? Right. The most deshielded ones. We're going to get some deshielding from chlorine, right? With that 3.1 shift. We're going to get some deshielding on the B from the phenyl group. We're going to get some deshielding on the E from the carbon-carbon double bond, the pi bond. But we're going to get some shielding on the C. Well, are we talking about carbonate? Indicated carbon atoms will be most deshielded. Okay. So the most deshielded carbon would be the one that has influences from both the phenyl group, the carbonyl group, and the double bond, the pi double bond. I think D would probably be the most deshielded. Yep. Now, no, that's hydrogen. Carbon, here we go. Subsequent effects. They got one that's just carbonyl, 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 carbonyl. No, that doesn't work. Coupling constants. Chemical shifts. Here we go. The most deshielded are the carbonyl carbons. And it doesn't matter what you're attached to. The most deshielded carbon is either the ketone or the aldehyde. Right. I'm trying to think like the authors do when they create these problems. Right. And of course, the evidence is there. So whatever they say must be true. Right? That 3.1 earlier must be true because they've got physical evidence for it. Physical evidence for the carbonyl on a ketone or an aldehyde is the most deshielded. Okay. So the answer is D. Number 40. Which hydrogen atom has the greatest chemical shift? Okay. Well, we don't have any double bonds, pure double bonds, right? The HA is too far away from that carbonyl. And HC is once removed from the phenyl. S is not electronegative enough to influence either HE or HD. So I think the greatest chemical shift would be the phenyl, the HB. Yeah, the HB. (41) What's the expected splitting pattern for the indicated hydrogen? All right, so if we look at this one, and then here, 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 and we're looking at this hydrogen right here. Actually, there are two of them. So what's the splitting pattern there? Well, the nearest one is this one right here, right? So this one is split by N, 2 + 1 is 3. Should be a triplet. And there's no influence from anybody else. So it should be a clean triplet, a symmetrical triplet. All right, 42. Some of these are similar questions. How many distinct signals are found in the C13 NMR for this one? This one here, there, and there. Oh, those are oxygens there. That's definitely heterocyclic. Okay, we're looking at unique carbon 13s. All right. This one is within the vicinity of that one, but this carbon is close to 2 oxygens. So that should be unique. These should be similar. That should be unique. This one is unique. This is a methyl group attached to another. This is unique. These two should be unique also. 7?
Yeah.
Yeah. 7 unique carbon signals. Did that make sense? Okay. Because I was thinking rather than teaching. Which nuclei in NMR active is NMR active and can be studied with NMR spectroscopy? All right. So if we look at each one, A, B, C, D, and E. This is that one. This one. Well, 16 and 32. All right, we need an odd number. Right. Here we have 1 proton. Let's do it this way. Make it easier. How many protons? How many neutrons? Right. 1 here, 1 there. This one has 2 and 2. 6 and 6, 8, 8, and 16 and 16, right? 32. That's even. This is the only one. There's odds. All right. Uh, 44. This is memory. Which factors are responsible for the large chemical shift in aromatic molecules? This is magnetic anisotropy. And 45. We've done several of these already, haven't we?
Yeah.
What's the expected splitting pattern for the indicated hydrogen? All right, what's its nearest neighbor? Nearest hydrogens are, there's no splitting pattern. I mean, you can't, it's not split at all. There are no hydrogens within 3 bonds. 1, 2. Yeah. Right. So it's a singlet. Yeah. There are 3 of them. There are 3 of those hydrogens on that methyl group, but there are no hydrogens in the vicinity. So there's no splitting. 46. Which compound has 4 distinct signals in 13C? All right. Should we draw these out? How are we doing on time? So, doing okay, aren't we?
Yeah.
All right. Well, let's draw them out. Like this. Okay, we got this one, this one here, and like that, correct? Okay, then 2 is that. 3 is tertiary butyl here, and then aldehyde. And then 4 is normal butane, and then we've got 5. That's 3. These are all parameters. And we're going here, there. Okay. Now we're looking for unique, chemically unique carbons, right? Which one has 4 distinct signals? This one would have, these carbons are alike, right here and here. This carbon is tertiary. This one's secondary, next to that oxygen. This one is unique, and these are the same. Right, so that's 5. That's not it. Right? This one's unique. That one's unique. But that one works. 2 works. These are the same. This one's unique, and this one's unique. This is symmetrical. This is going to have 1, 2. Right, so those only have 2 signals. This one has 1 here. That one's unique. That one's unique. That's only 3. All right, so we found our answer. Roman numeral 2. All right, 47. Which hydrogen atom has the greatest chemical shift? Well, let me see. Got bromine. There's a carbon, ether, and down here, that, That's that. This is a hydrogen. All right. This is a hydrogen. And oh, there's another one. Another one. Oops, that's a B. Sorry. There. And then this one is a hydrogen. Okay. So this carbon has 1, 2. There's another hydrogen here. Right, we're ignoring that one. This one has how many? This one's got a second one here. This one has another one here. That one only has 1, and this one has 3. But that's a methyl group. Okay. Chemical shift. Which one has the greatest chemical shift? All right. Okay, I think what we're looking at here is proximity to, well, we've got two possibilities: proximity to electronegative atom and deshielding from pi orbitals. And I think deshielding from pi is probably the greatest effect. Let's see. How many? Okay. Proton chemical shift. All right. So the greatest chemical shift. I'm looking at table 17.1. The greatest chemical shift is carboxylic acid. It's not there. We don't have any aromatics, right? So we can throw those out. Attached to an oxygen, 2.5. Simply attached to an oxygen is 2 to 5. Let's see. Okay, deshielding from the pi orbital is 5.3. All right, so that's greater than the hydrogens that are in proximity to the oxygen. Yeah. This hydrogen, this is 3.3 here. That's 5.3. If we could do that, we just go in and put the chemical shifts for each one. This one is once removed from a double bond. Once removed from a double bond is only 1.7. So that's a vinyl hydrogen. These are vinyl hydrogens. We want that hydrogen. I got that one already. There it is right there, 5.3. Yeah. Okay, I think we found it. It's this one. HD. All right. What's the expected splitting pattern for the indicated hydrogen? All right, we've got this hydrogen on a double bond and close proximity. What's closest proximity to that one? Well, there are no hydrogens to the right. There are 2 hydrogens to the left. So that means n plus 2 is 2 plus 1 is 3. So that's a triplet. Right. Off of that carbon to the left. Right. It has 2 hydrogens on it. So that's a triplet split. 2 adjacent. One of the 2 adjacent carbons is bonded to 2 hydrogens. All right. What does the acronym HETCOR stand for? HETCOR stands for heteronuclear correlation spectroscopy. It gives you a 2D NMR spectrum that provides information of which protons are attached to which carbon atoms. I don't like that question.
Scratch it.
That's what you would expect from specialists. We're not specialists. How many distinct carbon signals are expected from the following compound? All right, we got, starting from the left, we've got 2 equivalent methyl groups. Right. So that's one. Let's see, this is 50. So there's one. Then we get unique carbonyls. But the one on the left is associated with a tertiary butyl group. So I think those two, not carbonyl, those two double bonded carbons are different. So we got 2 more. Then we got a methyl group that's in proximity to the phenyl. That's another one. Then we have 2 that are on the phenyl group that are in proximity to the contact point. So that's another one. And then we have 2 more. Those are unique, and then 1 more. So that's 7. It says 9. Okay. Let me draw it out. I was trying to work from that thing. Maybe I need to draw it out to be certain. Okay, so I'll start from the other side. This one's unique. These 2 are similar. These 2 are similar. This one's unique. This one's unique. 6, 7. Oh, okay. 8. If I'd have done it this way, I'd have got it right the first time. Ah. All right, that was 50. 51. How many distinct signals, carbon signals, are expected from the following compound? All right, I better draw this one out too. 1, 2, 3, 4, 5. 51.
Yeah.
1, 2, 3, 4, 5. Then hydroxyl. And there and there. Okay. So this carbon and this carbon are attached to hydroxyls. Right? So they should have equivalent signals. These 2 carbons are the same distance away from both the hydroxyls and this tertiary carbon. So that's one. Oh, excuse me. These should be the same. 2, 2, 3, and 4. There we go. 4 unique carbon signals. All right, 52. Will a hydrogen nucleus have a greater energy difference between alpha and beta spin states in a 1.5 Tesla magnetic field or a 5.5 Tesla magnetic field? Well, the delta E, the distance between spin states between alpha, the distance between alpha and beta is proportional to the strength of the magnetic field. Right. So the greater energy difference between alpha and beta for the higher magnetic field. So the 5.5 Tesla would give you a greater distance between the 2, which means that it's going to absorb in a higher energy radio frequency, right? Shorter wavelength, higher frequency radio waves. That's one way that you can differentiate between hydrogens, or, well, in this case, hydrogen, is with the strength of your magnetic field. How many chemically distinct hydrogen atoms are in the following one? Okay. I learned my lesson. I better draw this thing. There. Oxygen. Right there, carbonyl, and then another oxygen. Here, right? Okay. Hydrogens. All right, so the hydrogens on these are all methyl groups. They're going to be the same. There are no hydrogens here. We have two hydrogens here. Right, they're going to be unique. There's no hydrogen here. No hydrogen there. That's 1, 2, 3. There's a hydrogen here, which should be unique. And then you have these methyls, which are, let's see, carbon. Right. Are these going to be the same here? This hydrogen, is it going to be the same as that one? No, I don't think so, because it's attached to a butyl group here, and this is not. So these are unique hydrogens here. Right, so should there be 4? Yeah, there are 4 unique hydrogens. We have to consider the environment. Is the environment the same? Then you can classify them as similar chemical shifts. Is that it? That's it.